But
live streaming is on.
oh,
I'm sorry about that. I didn't know it was going to do that.
Yeah.
Please go ahead.
Okay, but I am streaming my screen, right?
Yes, I can still see it.
Yeah. Okay. Yeah. So about the bridges, in other disciplines they build stuff and it just keeps on working. But in our profession, yeah, sometimes even with the smallest change, we can completely make it so the system crashes, and yeah, that's not something I like a lot. So I've been looking for years now for ways to write more and more correct and robust programs. So yeah, along the way I came across functional programming languages, and I've mainly used Elixir and Haskell. They each try to guarantee that you have more, that you can reason more about your code, that you have more confidence that it will run correctly, and they do it both in completely different ways. So Elixir has the fail fast approach. If something gets into a bad state, it will simply try and restart it again and start from a clean state and continue from there. And all the state is also isolated into small pieces, which makes your application, it makes it very easy to make it really robust. And in contrast, you have Haskell, that most of you are probably more familiar with. Haskell uses a lot of math in a lot of theory to guarantee that everything works correctly. And in Haskell, it takes the form of a really amazing type system. Normally if you structure your program correctly, you should not have any invalid states. And so, those are two different approaches. Since I came across functional programming languages, I haven't really looked back onto the more classical imperative or object-oriented languages, because it's simply so much harder to write correct programs. So I've lately been doing mostly Haskell. In my day job, I use a little bit of Elixir, but in my free time, I am learning Haskell, and still after a few years, and I'm digging deeper into it. And if you dig deeper into Haskell, you also end up in the compiler corner of the language really quickly. A lot of people write DSLs or compilers with Haskell. So I was also intrigued by it. Like, how do you do that? So I started digging deeper into that. Fast forward a year or so, and I'm writing my own compilers now. But it also makes you wonder, like, what does a compiler for functional languages look like? So for languages like C and C++, you have a lot of very good compilers. You have a lot of frameworks. Like you also have LLVM, which is like a common framework, like a common compiler backend with like a high-level kind of assembly that you can write, and then LLVM will take care of it and compile to all the different possible CPU architectures. While LLVM is really useful for languages like C and C++, it's not that well suited for more functional languages because there's a lot more abstractions going on, like higher order functions, for example. So I was looking into the fact, does functional programming have a compiler backend like that? Then I came across Grin. So Grin is an experimental compiler backend, a little bit like LLVM, but then focused for the functional languages. So the end goal is that you have one, that Grin does all the functional specific transformations, and then it gives it it passes it onto LLVM. And this will make it so that all functional languages, that if you write a compiler for it, you only have to write the first part, and all the rest will be handled by Grin. So then I was completely fascinated by how does Grin do all this. And underneath the hood, I saw that it uses Souffle. for writing a lot of complex analyses. So then I started looking into Souffle, what it is exactly. And I saw that it had an API, and I started tinkering with it. Before I knew it, I had a working prototype. So that's a little bit of the backstory. But what is Souffle exactly? So it's not a functional language. It's a logic programming language. So if you know Prolog, Souffle is related to that because it's a data log variant. And Datalog is a subset of Prolog. And logic programming languages, they are, again, very different from functional languages and also very different from object-oriented languages. Most of the time you end up writing a problem in the form of Datalog or Prolog, and then it will give you the solution for free. That's basically how those languages work. I will show you an example in a few slides. There's a lot of different data log variants, and they all have different use cases. But Souffle is focused on static analysis, so in compilers or linters, stuff like that. But it can also be used for security related things like firewalls or just graph algorithms in general. The nice thing about having a data log is it's really high level, so you can experiment with your algorithms really quickly. If you want to change something, you don't have to dig into the nitty-gritty details. It just stays really, you can reason about it on a really high level. And that's one of the strong points of Souffle. And the other one is that it is really super fast because if you, Souffle needs to be compiled, and it compiles down to very efficient C++. They do a lot of tricks to get the maximum performance out of it. Previously in the past, that was most of the time an issue with Datalog. If you try to use it in static analysis, the performance would be much, much slower compared to if you hand wrote the algorithm in C++, for example. But Souffle tries to bridge this gap and does a really good job at it. And the final thing about Souffle is that it is meant to be embedded in other languages, and that you see that also in the way you communicate with it. So you have two ways. You have a C++ API, or you can use CSV files to write data back and forth between Souffle and another language. Okay, so that was a short introduction of what Souffle was, but let's use it in action. So let's start with a simple example. So let's pretend we have a graph with a lot of nodes. So this example, we have we have one graph, but it's split into like two subclusters that are connected to each other. And my question to you now is just try to think of what the code would look like if you wrote this in your favorite language. How would you write an algorithm that finds all reachable nodes from another node? If you enter A, it should give you back B. If you enter the node C, it should give you back all these nodes as a result. And for most languages, this would already be quite complicated and involve probably keeping track of some state. It's not that straightforward. So what does this look like in Souffle? So before I go to the next slide, try to remember what I said about if in Souffle you try to write down the problem, and it will give you the solution automatically. So first of all, we need to start defining some predicate types or facts that we can use. So what I did was, if you look back at the graph, a graph can be described as the following. So you have a list of nodes, and all those nodes are connected to each other. You have edges between them. So in the first line here, what this is saying is create a new fact of with the name edge. It has two arguments, both are symbols, and a symbol is basically a string in other languages. You can have some other types in here as well, like numbers, floats, or even more complex data types. But let's keep it simple for now. So what this is saying is we create an edge fact or predicate between two symbols, and the symbols represent a node in a graph. Okay, so yeah, we can use this later to write down each of the separate facts, and then we can construct our graph that way. But we also need to figure out which nodes are reachable from one another. So I make another predicate for this, and I call it reachable. And now we have all the facts we need for this example. The last thing we need to do is we need to mark them explicitly as inputs or outputs, or both. And what this means is with this we can tell Souffle how the data will be used. So in this example, we will be providing the list of edges to Souffle. So that's why it's an input. And if you mark it as an output, then Souffle will, if you have a predicate, it will try to compute all of the results, and it will give you back those results at the end. But more on that later. Then it's time to write down some facts. You can either do this directly in Souffle or externally via CSV file or via the C++ API. And writing, if you write down the facts directly in Souffle, it's really easy. You say the name of the fact, and then between parentheses you add, you specify a list of arguments. And then it's followed at the end by a colon. So it's basically like a sort of sentence. This is saying there is an edge between A and B. And then you also have an edge between C and D, and so on. And now, after this block of code, we have described the entire graph. But yeah, we still need to figure out when are two nodes reachable from one another. And that's why I have the last piece of code. So this is a relation, and it's divided into two parts. So first we have the base rule or the base case. This is actually kind of similar to functional languages. And what this is saying is 2 points, X and Y, they are reachable. And you should read this as like a kind of if. So two points, X and Y, are reachable if we have a direct edge between X and Y. I don't know anymore if my webcam is on, but yeah, you either have 2 points directly connected, or there's a third point in between. And that's the inductive rule. Keep good track of the variables. So there's two variables, X and Z now. And what this is saying, 2 points, X and Z, are reachable if first we have an edge between X and a third point, Y, and if we can reach Z from Y. So you either go directly, or you have a point in between that you can go to. And yeah, that's also, I think, how you would explain it if you were telling this algorithm to somebody else. As you can probably notice, the algorithm is really compact, and that's probably also because it automatically handles the nested case for you. So it will try and recursively expand this to find all matching patterns. And what Souffle also does is that it keeps on looking for patterns or facts until it finds no more information. So in that regard, it's kind of like a fixed point. And as soon as it doesn't find any more information, it's done, and then you can collect the results. So that was, I think, 80% or so of the Souffle language all in one slide. So it's really compact, and I think also quite easy to learn. The hardest part is figuring out how to write these relations. But yeah, once you get used to it, you can write down really high-level algorithms really quickly. Okay, so this was Souffle. Now the question is, how can we bind Haskell to it? Because we want to use Haskell to control the Souffle. So first we need to start with some extensions. Yeah, this is not going to be a boring Haskell talk, I'm sorry. As you will see later, I will use some more fancy type level features to get more program correctness. But as an end user, you should not have to know what each of these extensions do. You just follow the example, and it's always the same. So how do you use my library? It's really easy. You only have one import, so you import. I would suggest importing it qualified. You import this module. What this compile part means, I will tell you in a few slides. There's also an interpreted mode, but basically you have to do one import and you get all the necessary functions and data types in scope, and then you can start programming with Souffle. Another important import is the GHC generics, because the library makes really heavy use of it. And it removes simply so much boilerplate. It's the first time I used it, but I will definitely be using it a lot more in the future because it's just so powerful. With the imports out of the way, we need to start thinking of a way, how can we describe to Haskell what the Souffle program looks like? So, for example, let's say that the program I wrote on the previous slide, that I saved this to a file called path.dl, and dl standing for data log. Now on the Haskell side, we also need kind of like a handle data type that manages the data log program. So that's why I create the path data type. It's really simple. It's a data type with a single constructor, no arguments, but you will see how I use it later. Once we have the handle, we can also write down the facts. As you can see, they have the same structure in data log. So in data log, it was 2 symbols. Here it is 2 strings. You can also use the text data type here. That's also supported. And something important here is that we have the deriving generic active. And this will enable us to do a lot of code generation in the following parts. So now we have this handle data type. We have the facts. Now we want to write down a specification of what the program looks like so that Haskell understands it. So for this, I created 2 type classes. So you have program and fact. And each of those has a specific job. So the program type class tells Haskell what the data log program looks like. So this is saying our path data type has the path data log program. It contains 2 facts, edge and reachable. The file is saved as path, and it will automatically append the .dl extension. So basically we're just writing down metadata of our data log program, and that will be used later on. So we described our program, but we still need to provide some information about our facts. So for example, edge in the data log code, if you remember, is an input, and reachable is an output. And the names are each in lowercase. And now that we specified all these things, now we have a complete description of what the data log program looks like in Haskell. we just need one last thing if we want to go back and forth between Haskell and Souffle, and that's serialization or marshalling. And yeah, normally this would be quite complicated, but because I use generics, I provide a generic definition, and it will always work for simple product types. By the way, all the facts in Souffle, they have to be on the Haskell side. There are always simple product types, so records. And the way I created the generic instance is if it finds a simple product type, it can automatically derive the code for that. So that's why you get two empty instance definitions. And this is all you need to serialize the data back and forth between Souffle and Haskell. Okay, so we have a complete description of the data log program in Haskell. We know how to serialize data back and forth. So now we can start writing actual programs with it. And yeah, there's one function that does this, and that's run Souffle. It takes the handle data type that we created earlier, and then it will try to start up Souffle. This can either fail or it can work. And for example, if it doesn't find the Souffle program, or if it can't find the compiled C++ file, yeah, then it can fail, and that error needs to be handled. Yeah, right now this is done via the maybe data type. So if you find nothing, you need to handle the error. Right now I do this, yeah, really straightforward with a print statement, but yeah, most likely you would have to make this a little bit more complicated in your application. But that's the error case. For now, not that interesting. If it works correctly, you get back a new kind of handle, and that's used to interact with Souffle. And how do you interact with it? You can either add facts. So yeah, I have two functions for that. You either add one fact directly, or you can add an entire collection of facts. Yeah, I think this is quite straightforward. Yeah, this can be a list, a tree, can be any kind of foldable data structure. It's all supported. And this way you can really easily push facts from Haskell to Datalog, and you can give the system more information. Okay, so we can add facts. Then we need to tell Souffle to actually do the computation. That's not automatically. So you have to do a manual step here, and that's with the run function. And then it will take all the input facts that it finds. So either directly in the Souffle file or programmatically via Haskell. It will take all those facts, compute all extra facts it can find. With it, and then we can collect them. And for this, there's two functions again. So you can either query all the facts, or you can look for a specific fact. And each has their own use cases. So yeah, most of the time you either want to get back all the results, or you want to look for a specific one. And the specific fact, if you enter that, Souffle can be smart and optimize that. And that, it can be a big performance benefit if you have a large result data set. Also what you might notice is that I have type signature here, and that's only necessary because I immediately print out the results again. So Haskell has no information of what kind of facts this should be. So it doesn't know, is this reachable or an edge fact, but it also doesn't know, is this a list, is this a vector? So you have to provide the type annotation. But this is only in the example code. So in real code, you would probably have a function that takes a vector of reachable or something else. And then Haskell can automatically infer what the type of results is. Also, if I say that this is a list, for example, then the get facts function will be smart and will give you back a list as a result. There's a little bit of type type level programming going on here. And yeah, that's it was a little bit confusing when I first started to get it to work, but once you get the hang of it, it can be a really powerful technique because the get facts function is now really versatile. Anyway, that was the complete example, and yeah, let's talk a little bit more about the features. So as you noticed, the library is really small. So there's only 6 functions and 3 type classes, and I used them all in the previous example. And that's also an active goal of mine, to keep it as small as possible. And yeah, all the rest is basically automatically generated for you thanks to generics. And yeah, I think that makes it easier for developers to use. Then about the 2 modes of operation. So Souffle can work in 2 different ways, and yeah, I called them interpreted mode and compiled mode. What this means is, compiled mode is if you compile your data log code ahead of time down to a C++ file, and then embed that directly in the Haskell code. Opposite to that, you also have interpreted mode. And interpreted mode is when you use the Souffle interpreter during runtime, so that it takes in the data log file and then it compiles it on the fly, and then it will use CSV files as input and output. Those are the 2 different modes. What I did was, you saw earlier that I only have 1 import. And if you change that from language.souffle.compiled to language.souffle.interpreted, then you get a completely different mode, but the API is identical. So that makes it really easy to swap between the 2. And that's good because the interpreted mode is better suited for development. So you can iterate really quickly. You don't have any compile times. You can just keep on iterating on your algorithm until you have working program, fully tested and everything. And then you can swap over at the end to the compiled mode. And then you get the much better performance that you would expect from a C++ program. So I try to support both modes, so you get the best of both worlds. I use quite a bit of fancy type level features in Haskell, but that's not always the best for compile time errors. So I try to mitigate this in 2 different ways. So first of all, wait, 1 step back. So I have the fancy type level stuff, but I want to hide the complexity, and for this I have the custom type errors. I will show you what those look like on a next slide. I use the type errors pretty package for that. It's on Hackage and it's really nice. It's made by Dmitry Kovainikov, I think his name is, from the Kowainik team. It's a really nice library to use, and you can make really beautiful compiler errors, hopefully to make the developer experience easier. So that's the first thing I do with all the type level information. And another thing is, you can make really customizable compile time checks because we have those type classes like the program type class and the fact type class, and they're basically a bunch of metadata about the Souffle program. And because it's all available on the type level, we can all use this during compile time. So I can make really strict functions, and hopefully I can make it so strict that you can only use it in the right way. I explained it a little bit backwards. So let's get back to the custom type errors. So what do they look like? So at the bottom is the code that I wrote. So if you remember, reachable is an output fact. So you can't use it as an input, which is what add fact assumes. So then you get an error message, and this part is the custom part. So I wrote this down somewhere in my library, and it says, you tried to use reachable as an input, but it is an output fact. So and then what I always try to do is I try to give them a hint for saying, you might have wanted to do this. It's kind of difficult to anticipate all possible solutions, but I try to make it so that the error message makes the developer think and hopefully figure out what the problem is. So here I suggest to change the direction to either input or input-output. But maybe the developer just made a typo or made a mistake, and this should be edge instead. That's a little bit harder for me to anticipate, but I try to explain it as good as possible in the error messages. And so the first bullet point in the list is my custom error message, and then the rest of it is like you would normally expect in Haskell, saying, oh, it's in this expression, in this do block, and so on and so on. So that's one example. Another example is, so I was talking earlier about all the data types having to be simple product types, but if you try to make it a sum type, then it will also complain, because I also guarded against that. And then you get here the message, I cannot derive this for a sum type, only product types are supported. And you get another message if you forget to add any arguments here. And you can do a lot of things wrong, but I try to cover them all so that you can use the generic mechanism only in the correct way. And if there's a gap there, then please submit an issue. That's the compile time checks. And with that, I try to make the developer experience as good as possible, even if you have really complex type level features in your library. Another completely different thing is that, because Souffle Haskell, if you compile the Souffle code down to C++ code, it will make your Haskell code a little bit difficult, a little bit more difficult to compile. And we want to hide that from all users that depend on your code. So I try to make a schematic of it. So you have first my library on the right. Then you have some dependency using it. So it will have an algorithm compiled down to C++. But you don't want the package that uses the dependency to also require all the necessary C++ headers from Souffle. So what I did was, Souffle Haskell also bundles all necessary C++ files into the Haskell package itself, so that everything that depends on this dependency, it doesn't have to know, it just can write down this is a dependency, and then it will be able to compile it, just like any other Haskell package, basically. That only works for compiled mode, by the way. If you didn't do that and you are still working in interpreted mode, then the final package still needs the Souffle interpreter at runtime. So what I would suggest, this anyway, just for performance reasons, but always when you're done, compile it down to C++ and embed it in your Haskell code. That's also explained in the README of the GitHub repository how to do that. So before I continue, that was basically the end of the talk for, I think, up until a few months ago. But like I said earlier, I built quite a few compilers, some small, some big, and some of them are DSLs. And then it gets you thinking: is it maybe possible to write a DSL for Souffle? And I started experimenting with that, and I came to some nice conclusions. And that's what I'm going to be talking about next. So. First of all, we have the data log snippet from in the beginning. I removed the hard-coded facts, so right now we only have the the part where we describe which fact data types we have, and then the actual relations. And then the question is, it's like an experiment we can do with ourselves. Can we rewrite this piece of data log code in Haskell? So let's do it step by step. First of all, we have this part where we describe the fact data types, and also if they are input or outputs. But actually, we already have all that information on the Haskell side via those type classes that we used earlier. So what does this look like? It looks basically the same as before. We have to derive one extra type class. The default implementation is fine, but that can be used to further tweak the performance settings. But that's not that important for now. Like before, we just write down our facts. We write down for each fact, is it an input or an output? What is the name on the data log side? And what we want to do now is we want to turn that around. So before we went from data log to Haskell, but now we want to go from Haskell to data log. And all the information is structured or it's like metadata for the type. So if we can think of a function, let's say we want a function that creates a predicate for a specific type. So this is a type application. What this basically says is, predicate for is a function with no value level arguments, but it has one type level argument. And this says, if you can you give me a predicate for the edge data type? It will give you back a predicate, and inside, there's some other value. What this is exactly, I will tell you in the next slide. But if we can think of a way to do this conversion, then we can go from all this type level information to value level information. Okay, so let's continue with the experiment. So what we need to convert next is all the logic parts, so the relations or the facts. And for this, we can use Haskell again in a really cool ways. So Haskell has overloaded literals, so you can write down a 5, and in most languages that would just be a number, but in Haskell it can be any overloaded data type. And then, if we just have functions and combinators, so functions combining other parts together, then we can create the logic. And how would this look like? So if we have those predicates from before, so edge and reachable, then we can start to use those to glue together different parts of the program. One difference that we have is we need to manually introduce all the variables. So you have X, Y, and Z. After we introduce them, then we can use them in the predicates. And this is valid Haskell code. I tried to make it look as much as possible like the data log code. But you can tell it's Haskell from the do keyword here. And also the operator here is different. But in Haskell, again, you have custom operators. So I defined this operator in terms of this operator. So it's really straightforward. Haskell is really nice for making a DSL. But there's still this part, like how does this work? And it might look like something that you're not used to in Haskell, but basically reachable is a function, and it takes a tuple of arguments, and the structure of the tuple is based on the type of the fact that you pass in. So if edge had 3 arguments, then you would have to create a tuple of 3 values here as well. This together forms like a kind of a part of a data log program. And I do the same trick again here. And then I have this operator, and this operator glues together the 2 parts together to form one part of the predicate. And I just keep on repeating that trick. So if you have multiple, constraints in your rule body, then you need to have a do block, because that's how Haskell works, or how you can get the syntax as close as possible to data log. So, but it's always the same trick. So, yeah, here it will create a part of data log code, and here it will create another piece, and then it will be all glued together inside this do block. And then you can use this operator again to glue everything together. And the result is something that I think looks a lot like data log, but it's completely in Haskell. And as you also probably saw before, the example itself is also in a do block. So with some clever use of monads, you can create a fully custom DSL specific for data log. Okay, that's a lot of information probably. So yeah, basically what this shows is we can write down all our data log code in Haskell. And the way that this is done, it allows us to do some really cool stuff. So we can do meta programming now. And that's really nice because, maybe you noticed, but in logic programming, there's quite a lot of repetition. So you have to write down snippets of code like this a lot. And the question is, if we find patterns in those, can we make it so we write it only once and do it polymorphically or generically, so that we can reuse it later on? And the answer is yes. Otherwise, I wouldn't be asking the question. So before I show the optional type signature, which is really complicated, let's first take a look at the helper function I'm going to write. So maybe first a step back. The way logic programs they often have they often are defined in terms of properties. So in this case, you could describe this as a kind of a transitive property. So you either have a direct relation, or you go to a third point, and via the third point you can end up at the end point. And that's transitivity in a nutshell. So let's try to write this down generically. And what would this look like? So we are not working anymore with edge and predicates. So just a generic predicate P1 and a predicate P2. Again, we need to introduce variables here, but we don't know what the variables mean anymore. So we have to make them really generic. You can't write down a specific name for it, because you don't know what this code is going to do yet. Once you have the variables, now we can glue together the program like before. And this is exactly the same as before, but this was previously reachable, and P2 was previously edge, and they're now completely swapped out. And it will work now for any predicate. So what we did now, this by itself is enough to get it to compile in Haskell. And this will work for any two predicates that are related to each other in this way. But if you want to write down a type signature for additional documentation, that's also possible, but it's slightly more complicated. So how would you read this? First you need to read the last line here. So what this says is you take one predicate P1 and you take another predicate P2, and it will generate, the end result will be a part of the DSL. So it will be a piece of data log code, basically. Ignore all those type variables at the end. But basically, you have two predicates, and you will combine them together to form a piece of the DSL. So like a DSL fragment. And if you write down just this, then Haskell will not be satisfied, because you have two separate predicates, and Haskell will not know that they are the same, that they have the same structure. So I wanted to say the same type, but that's not true, because edge and reachable, they can be different. But what's important is that the structure of a predicate, that is the same. So here I do some tricks with type families. So I have a type family to get the structure of a data type. It will give me back a list of types of all the arguments in the constructor. So what this basically says is the structure is, it takes 2 arguments, and all the arguments have to be of the same type T. We don't know which type, but they have to be of a type T. And if you add that to the signature, it's still not enough, because Haskell needs to know that the structures are the same. And we do that with this. And here we say that the structure of P1 has to be equal to a structure of P2. And if you do this, all these constraints together, then Haskell will finally be happy, and it will type check. And yeah, right now what we have is we have a function to easily describe the transitivity property. So let's use this in an example. So again, we create a TSL fragment. And also, like before, we can create a predicate for edge, we can create a predicate for reachable. And then we say, yeah, reachable is transitive via edge. So I think it's immediately obvious that we are now reasoning on a level higher than before. And yeah, the code becomes even shorter, but it does become a little bit more complex to achieve this initial result. But yeah, let's continue. That's not the only way we can do some meta programming. So I was also doing some other coding in Souffle a while ago, and yeah, basically it boiled down to the simple thing. I had to write down a lot of constraints for different variables. So if you take a Sudoku, for example, every number in the row needs to be different, and every number in a column needs to be different, and also every number in like a square also needs to be different. And in other logic languages like Prolog, that's most of the time you have a helper function there that easily adds that constraint, but Souffle does not have that. So yeah, and what you end up having to do is you have to write out each of those constraints separately. So if you write down number 1 not equal to number 2, number 1 not equal to number 3, and so on. If you do that for all the numbers in the row, you end up with a massive list of constraints. I think it's 36 or so, because it scales up with the amount of numbers in the row. And yeah, if you have to write down 36 constraints, you have to, first of all, it's really tedious. You have to write down a lot, but you also have to make sure that you don't make any mistakes. So it's really easy to add duplicate constraints, and Souffle will not warn you about it. So yeah, it's also really error prone. And then the question is, can we use Haskell to solve this? I figured out a way. It's the following snippet. It's really short. So first we need some helper imports, and then we can start writing the solution. So what I did was, first I wrote a small helper function that computes all the possible combinations. So if you have a list of elements, we don't know which type, then I want to get back another list with tuples containing all the possible unique pairs. After some searching with list comprehensions, this is the shortest I came up with. So you have I use the tails helper function here, and what it does is it gives you back all the possible tails of a list. Sorry. So if you have the list 1, 2, 3, it will give you back the list 1, 2, 3. Then it will give back the list 2, 3, then 3, and then the empty list. And for each of those lists, I want to destructure it again, because each time we are interested in the first element, because we want to say the first element is not equal to all the other elements in the list. And the other elements, we have to destructure those again in separate values again. So now we have 2 values, x and y. And if we return all those, then we get all the possible unique combinations. So what does this look like? So if we have a list of 1, 2, 3, then we get back a list of 1 and 2, 1 and 3, and then 2 and 3. And then, for example, not 2 and 1, because that's the same as 1 and 2. So we have a really short helper function. And I think it's also important to note here, this is just Haskell, nothing special going on. It's a pure function. It knows nothing about Souffle. It's all about generating combinations, right? So now we can use this to generate some code. So I call this distinct vars. So this will make sure that all variables are distinct. The type signature shows a little bit of the internals of the library. So a term is basically any value in my DSL. So also variables are a term. I have a list of variables, and what it will generate, and what the function will return is a rule body. What those type level arguments mean, ignore that for now. But basically, we take a list of variables and we return a rule body or part of it. So what do? First, we compute all the possible combinations. That's really straightforward now that we have the helper function. And now we need to go over each of the pairs. So let me explain it from the bottom one, and trust me if I say that the line above is the same. So we go over each of the variable pairs with traverse, and then we have to give the lambda function that gives you a pair of variables each time. And then we can use an operator defined in the DSL to say those variables are not the same. And the end result will be, if you add this function to another part of the DSL, to a DSL fragment, if you give the list of variables, it will automatically generate all the possible combinations and then say each of those, they are not equal to each other. And then, you go from 36 constraints to a single line of code. So I think that's a huge win. So what are some of the benefits of this approach? So first of all, the FP part and the logic part, they're now both in Haskell. So that's one less language you have to deal with, because otherwise you have to deal with Datalog, Haskell, and C++, and now it's only Haskell and C++. And also the nice thing is the Datalog program itself is a Haskell value, and Haskell is really good at transforming values via functions. So what this basically means is that we now have a way to transform entire Datalog programs, which is really powerful. And this allows us to do, we can write down new concepts via code generation. So the previous example was an example of that. But we can also have a lot of code reuse. So because Haskell has an amazing type system, it can automatically compute the most generic. If we write down a predicate generically, Haskell can figure out the most generic type for that, and that will also mean that we can reuse it in as many places as possible. So that's also really powerful. But what are some of the limitations or the cons of this approach? So not everything of Souffle is supported. So like before I said, this is maybe 80% or 90%, but there's a small part that's not supported. But if you need that right now, I would suggest just doing the approach that I used in the first part of the talk and use an external data log file. Then you can use all the features of Souffle. But currently that's not supported yet in the DSL. Also, what you need to watch out for is that not all errors are captured in the type system. I try to go really far and capture as much as possible. But some errors that are detected by the Souffle compiler, they're just really difficult to capture in Haskell, or I haven't figured out a way to do that properly yet. Be careful with that. It sounds a little it sounds a little bad, but if you end up compiling the Souffle to C++ anyway, then you will get the errors. But what I try to achieve is that you get all the errors up front, so that you get a much quicker development cycle if all the mistakes happen on the Haskell side of things. So yeah, it's not that serious, but I still try to figure out how to capture as much as possible in the type system. And yeah, another negative thing about this approach is, I think all of you will agree with that, is that it is much more complex. So yeah, you can start to reason about a much higher level about your code, but yeah, it's much more complicated. And yeah, there is an initial learning curve that you have to overcome. But after that, yeah, you have a lot more power. Yeah, so that's all about the library. Now, let me explain some of the projects already using it. So yeah, the funny thing is this is not true anymore since last week. But I used to use Souffle Haskell in my library itself to compute the minimal set of C++ includes, because that's also a transitive kind of thing. So you first start from one C++ include, and then you branch out to all the other C++ includes. Yeah, and I had a Haskell program that called out to Souffle for this. But yeah, last week I figured out a way to do it even more easily. So yeah, I had to swap it out. But there are other projects as well using Souffle. So there's the Grin project I talked about earlier. Right now it's not merged in yet. It's in an unmerged pull request, but that will probably be merged in once they do. Yeah, they're working on a complete overhaul of their of how the repository or how the code works internally. And once that is done, then Souffle Haskell can more easily be used. But they already tried a first experiment with it, and on one of their heavy algorithms. And what they saw was, compared to the Haskell algorithm that they first used, they already see a 40 times speed up. And that's all thanks to Souffle compiling down to really efficient C++. So that's also, yeah, I'm really hopeful about it. So yeah, compilers often have really heavy algorithms, and if we can optimize those by such a big factor, yeah, it's noticeable. So yeah, it makes me really hopeful. And yeah, if you are interested in Souffle and want to see how it can be used, yeah, I would definitely suggest looking at this pull request. It really goes all the way. Another project, also from the Grin team, is GHE WPC. So it's a whole program compiler for Haskell. Yeah, it's a part of the tooling they need to develop so that it becomes easier to write the Grin compiler. And yeah, again, because the way of the compiler works is it takes in all possible Haskell files that it finds in the code base, and it tries to compile it down all at once into a single executable. And as you can imagine, the algorithms are really heavy there, and they also use Souffle there under the hood to do the heavy lifting. And so they also use Souffle Haskell now to easily call the Souffle code from Haskell. And yeah, who knows? Maybe you have some cool project ideas that could use Souffle Haskell. So if you have any ideas, please let me know. Maybe we can figure out some cool things together. Yeah. So yeah, in conclusion, so I hope I convince you that there's some kind of synergy going on between functional programming and logic programming. So in a way, yeah, functional programming is all about data and transforming that data via functions. And on the other hand, logic programming, so data log is all about you have some input data and you try to compute more and more data. And so if you look at it a different way, data log is kind of like the fuel to the engine, right? So the more data you have, the more your functions on the functional side can do with it. And yeah, also I think there's many undiscovered opportunities. This is really unexplored. So yeah, I keep finding more and more use cases the longer I think about it. So I would, I would urge you people to also start thinking about this. This is some really powerful stuff, and I think we can create some really cool applications with it. Yeah, another thing is the Haskell type system is really amazing. Some of this stuff is simply not possible to program in other languages, like the custom type errors, the custom type level checks. I don't think there's a lot of languages that can do that, but Haskell is one of them, and it makes programming in it really amazing. But one final thing, I didn't talk too much about it, but integrating Haskell and C++ together